give you an official welcome for today's presentation. Here's the plan for today and for next week. We're going to cover two topics that are already scheduled. One is internal radiation dosimetry. And in fact, let me share my screen so you'll be able to see the first slide here. And the second topic that we're going to cover will be personnel monitoring devices. We will do that right after this one is completed. We'll take a short quiz on each one. And then I mentioned last week that if anyone had questions about anything that we have covered before or would like a quick review, we would do that. And in fact, I got a very lovely email from one of the ladies in the audience who wanted to have a little review of half value layers, 10th value layers, and similar topics. So assuming we have time, we will dive into that. So let's go ahead and officially begin. We're going to talk today about internal radiation dosimetry. And this is important for a lot of reasons. Number one, you're concerned about your internal radiation dose for an occupationally exposed individual. You all are going to be working with radioactivity all day, every day, 5 days a week for who knows how many years. So you're certainly concerned about your internal dose. Also, we are equally or perhaps more concerned about patient radiation, internal radiation doses. So we want to have an understanding of what dosimetry is and how we measure it and what are some of the values that have been set by the Nuclear Regulatory Agency. So I want to start out with a few anecdotal things that are really very interesting. Madame Curie, as you probably know, was the discoverer of radium, and this took place approximately the year 1900. Out of a couple of tons of pitchblende ore, Madame Curie was able to isolate a couple hundred milligrams of radium. Now, you and I would not like to even be in the room with a couple of hundred milligrams of radium because it's intensely radioactive and producing lots and lots of gamma rays. But back 120 years ago, no one really knew much about dosimetry or the effects of biological radiation. So Madame Curie's professor was so proud of her discovery that he put the radium in a glass vial, sealed it up with an overseal, and carried it in the breast pocket of his coat close to his heart. And Madame Curie herself carried test tubes of radium in her lab coat for a very long time. It turns out that Madame Curie ended up with leukemia at the ripe old age of about 60 from her excessive exposure to radiation. And back then, no one knew how dangerous it was. In fact, when they reported their results, some of the other researchers said, hey, that's very interesting. Radium can cause radiation damage and skin burns. And so they took weighed pieces of this new metal, perhaps 1 milligram and 5 and 10 and 20 and 50, and they taped it to their arms to see how long it took to get an erythema or reddening of the skin. We would never do anything like that today, considering our knowledge of radiation effects. But back then, they were just doing basic research. In fact, the discoverers of the early X-ray tubes used to hold their arm out in front of an X-ray beam to determine the output of their X-ray tube. Again, something we would never even dream of doing. And so they irradiated a patch of skin, and the dose that produced a reddening of the skin, that's called an erythema dose, was about 700 rems. Now, that's a huge amount of radiation. I think from the NRC regulation lecture, you'll probably recall that I mentioned that an LD 130, a lethal dose where 100% of the people would die in 30 days, is about 550 rems. This is a much higher dose than that at 700 rems. But keep in mind, this is not a whole body dose. This is simply a skin dose, and it really potentially cause very bad skin damage down the road. but that's nowhere near enough whole body dose to be harmful to anyone. Many years ago, we're going back to I'll say about 1915 to 1920. There are stories that people have heard multiple times about the radium watch dial painters. I actually looked on the internet and I found a photograph of these ladies who were painting watch dials. And what they did was that they took their brush, dipped it in the radium solution, and then used their lips to shape the brush. Here's actually a photograph of a lady over here shaping a brush tip. Here is what this looked like in the factory. They were called radium girls. And it turned out this was a woman's job back then, not because men refused to do it, but it was World War I and men were gone. They were overseas in Europe fighting a war. And so it was very common to have a factory full of radiation workers who were painting the watch dial faces. Here's a picture of a watch in a darkened room, and you can see that there are the 12 little rectangles for each of the hours, and the white part on each of the clock hands. And in fact, the reason that this was of interest is there were two reasons. Number one, the soldiers in Europe in foxholes couldn't see what time of the day it was, and they needed a watch that glowed in the dark. And number two, for those rich people who were still back in America, they wanted to know what time it was when they couldn't sleep at 3 o'clock in the morning. And so there's a relatively short period of time where these ladies were active. And think about the following. The risk of developing primary bone cancer in the general public is approximately 3 per 100,000 people who develop primary bone cancer. In this group of ladies, it wasn't 3, it was actually 35,000 out of 100,000. There was a 35% risk of developing bone cancer because of this occupational exposure that they had painting watch dial faces. And so that's a huge, huge number. And once people recognized that risk, they immediately shut that industry down. Here's something that my family personally has had to deal with. When my wife was a child back in the late 1940s, she had neck irradiation. Children had their neck irradiated back then for two reasons, either for tonsillitis or for an enlarged thymus. We're not sure why she had it, but one of the effects down the road is that neck irradiation causes two things. It could cause thyroid cancer, which fortunately did not happen, but it also causes the development of parathyroid adenomas. And over these many years, she has actually had 4 separate surgeries for 4 separate parathyroid adenomas caused by childhood irradiation. What we've also learned is that adults who have neck irradiation really don't have any of these side effects. They are basically the juvenile thyroid that's at risk and not the adult. Now, I am not a radiobiologist, so I can't do too much more than read parts of the slide to you, but there's one thing we're certain of. No one has ever been able to document a threshold level for radiation damage. We can't say, for example, that 25 rems is dangerous, but 24.9 is not. There's no number like, we know the boiling point of water is 100 degrees centigrade. We don't have a number like that. It depends on, are you male or female? Are you a senior or middle-aged or a young person? There's so many variables that there is no threshold level. There's just no number. One of the things we also know is that the risk of radiation is never zero. And I have heard a technologist or two over the years tell their patient, oh, there's no risk from this procedure whatsoever. Nothing is going to happen. Well, that's in general, that's true. We're never certain. There's always some risk for radiation, especially therapeutic radiation, but also diagnostically. So technologists should never be telling patients that the risk is zero. They could tell them the risk is very, very small. It's immeasurably small, And it's equivalent to perhaps having a few chest x-rays. Now, some other things that we've learned about radiation dosimetry would be the following. The rate of induction of cancer and other abnormalities is so low that it's almost impossible to measure. If a person develops cancer, there's no way to say your cancer was caused by X. We simply can't do that. If we take a look at 1 million people, we might be able to find a trend, but in an individual case, we can't. The time between exposure and symptoms is inversely proportional to the dose. If you get a really high dose, you're going to have symptoms in a very short period of time. If you get a moderately high dose, it'll take longer. If you get a very small dose, they may never appear. Also, this third bulleted point here, this is what we base radionuclide therapy on. We want a low exposure rate. We want the body to be able to repair damage to DNA. And that does not happen when it's a high dose or an acute dose. And so when we are performing radionuclide therapy, let's say on a hyperthyroid patient, we want a T effective measured in days. We want to deliver that dose, that radiation dose, over a lot of days, 30, 50, 60. We don't want it all in one day. The patient wants it all in one day because the patient doesn't feel good, wants to feel better. But we don't want that. It's not desirable. We want that low exposure rate. Now, you're all familiar with the ALARA concept. Back in about 1975, this concept was developed as a way to minimize radiation dose to radiation workers. It really has very little or nothing to do with patients because we can't lower a patient's dose below the prescribed dose. That's really the only way to minimize patient dose. We just can't do that. So in 1996, this ALARA concept became mandatory, and implementing it is part of the radiation safety program in all hospitals. In fact, the ALARA concept has to be written up and included in the policy and procedure manual. What it basically does is it heightens the awareness of technologists so that they are very careful and keep radioactivity in lead all of the time, except that brief moment when they have to take it out to draw a dose or inject the patient. And I think you all know that one of the parts of the ALARA policy is to mention what our MPD, our maximum permissible dose is. This is only for radiation workers, and it is 5 REMS in any given year. Now, if I were asking you your board question, let's see if I've got it. I don't have it here, but how many millisieverts would 5 REMS be? Keep in mind that we have to convert REMS to millirems, and then since the prefixes are the same, millirems and millisieverts have the same prefix, milli, then we can work the problem. So if this is 5,000 millirems, how many millisieverts is that? Please feel free to unmute yourself at any point in time and shout out an answer. Anybody know?
Would it be 50 millisieverts?
Perfect, 50. 5,000, and since the sievert is 100 rems and a millisievert's 100 millirems, we take the 5,000 and divide it by 100, and we come up with 50. So we have 5,000 divided by 100, that's 50 millisieverts. You should expect a conversion like that on your board exam. I would not be at all surprised to see it. Also, for our families, their MPD is only 100 millirems per year. So we're permitted 5,000. That's 50 times what our families are permitted. And also for our hands, we're permitted 50 REMS. There's no bone marrow in our hands to speak of, and so the risk is minimal to have your hands in a beam. In fact, the people who are more at risk than anyone is radiologists who have their hands in a fluoro beam, and those are the people who get high hand doses. Now, the NRC has regulated that many of the records that we generate on a daily basis, dose records and prep records, we have to keep those for 3 years. But for monitoring of people, The records have to be kept for a lifetime. We are not permitted to throw them away until the NRC says you can decommission your license. Otherwise, radiation safety dosimetry records have to be kept forever. They could come and say, show me your records from 40 years ago, and you have to be able to do that. Now, ionizing radiation includes a lot of things that are coming out. Though there are particles like alphas and beta minus and beta plus particles. There are photons like gamma rays and X-rays. And in many cases, water, the water molecule, it's ubiquitous in the body, is involved. When radiation hits water molecules, it can cause what's called free radical formation. That creates charged particles, which can damage DNA and possibly be involved in the induction of a cancer of some kind. Depending upon the dose rate, the tissue may or may not be able to repair itself. That means that's why we wanted to give that very low dose rate thyroid therapy over many, many days. Otherwise, the damage would be too high and it could cause all kinds of problems, not just cancer, but other things. And in fact, here are just a few of the effects of ionizing radiation that are well known. Acute skin burns and dermatitis, alopecia, that's hair loss, if the dose is high enough, induction of cancer, and genetic effects. Now, we're going to take a look at the more technical aspects of internal dosimetry. And so one of the things you'll bump into if you probe in this area is that there are data that are called input data and output data. The input data means what can you learn by looking at the decay scheme and the chart that goes with it. The output data includes all the possible contributions to the internal radiation dose. And you're going to be amazed at how many of them are, even if the decay scheme is very simple, like that of technetium. Included in the output data will be things like all the different X-rays that are coming out and all the different electrons, internal conversion electrons, or ICEs, and Auger electrons. So let's take a look. There is a booklet called the MERD booklet. MERD is a Medical Internal Radiation Dose Committee. That's a part of the Society of Nuclear Medicine. And I took this chart from the MERD book. Now you can see that technetium has a very simple decay scheme. There are 3 gammas. This is the highly excited state, this top line. Gamma 1 drops from the highly excited state to an intermediate excited state. And then it stops for a brief microsecond or so, and then it proceeds to ground with gamma 2. Now let's look at the numbers. Gamma 1, which occurs 99% of the time, is only 2 keV. Is there any hope of imaging a 2 keV gamma ray? And the answer is no. That is so non-penetrating that it will never escape the patient's body. And in fact, we don't like it because it doesn't escape the body and it confers a radiation dose. How about this one though? 140.5, 98% of the time. We love that one. That's the one that we image with. And this one, 142.7, almost identical to this one. And we would certainly capture it in the imaging window. But how useful is this? Not very. It only happens a little over 1% of the time. So sure, we'll take it, but it's not really very helpful. So you're looking at a very simple decay scheme. And you might think, well, how many contributors could there be? I only see 3, 1, 2, and 3. Let's take a look at the list. Hard to believe, but there are approximately 20 different contributors to the internal dose. Now, if you look at the percent abundance, many of them have 0 point something, like here, a bunch of 0.3, 0.03, and some more down here. Many of them are insignificant because their abundance is low. But look what's in the chart. We have gamma 1 and an internal conversion electron associated with gamma 1. We have gamma 2 and 3 internal conversion electrons associated with gamma 2. Then we have gamma 3, which has 3 more ICEs. And then we have here 5 different characteristic X-rays coming from the K and L shell. And how do we know the characteristic? Because over here in column 3, there is a finite energy associated with each one of those. This one, for example, is 18.4 keV. It's not a broad spectrum of energy. It's a characteristic energy. And then associated with these 5 X-rays are 5 Auger electrons. And so we have 20 things to worry about, minus the ones that are 0 point something percent. We don't worry about those too much. So you can imagine if this decay scheme has that many contributors. Think about iodine 131, which has not 3 gammas, but 19, and not 0 betas, but 6. And so this chart would be pages long. It would not fit on one slide, not at all. Now, this committee has developed something that they call a standard reference man. And they define this as a bisexual construct. Now, lest you think there's something funny about that, all that means is that this standard reference man, or I should say standard reference person, refers to all humans. It doesn't matter whether you're male or female. And yes, we know we physically look different, but when I show you the picture, you'll understand why. This is basically a 70 kilogram phantom into which one can place, let's say, a plastic liver with 1.00 millicuries of technetium. We can determine the dose in other parts of that body. So here is our reference man. This cylinder up here represents the head and neck. This longer cylinder here represents the chest, abdomen, and pelvis. And this final cylinder down here represents the lower extremities, the legs. And that's what the merged standard reference man looks like. So because it truly is not physiological in nature, it's not going to be a perfect kind of phantom, but it is very helpful in determining radiation dosimetry factors that go into our equations. Now, we're going to take a look at a couple of equations here. No one on your board exam is going to ask you to work a problem with this. The question you would get would be something like this: upon which of the following factors is internal dosimetry dependent? And here they are. C0 means what's the concentration of the isotope in the target organ in terms of microcuries per gram. The T effective, we all know what that is. The T effective, just as a quick refresher, means how long does it take for the radioactivity level of something that's alive to be cut in half, because both elimination of the isotope and radioactive decay are taking place. We care a lot about the fraction of betas and gammas emitted. If the fraction of betas and gammas is 1%, it's going to contribute essentially nothing. But if the fraction of decays would be 95% or 0.95, that makes it ultra important. So that goes into the equation. Betas are not monoenergetic. They have a broad spectrum of energies. And so what goes in here is the average beta energy. That's about 1/3 of the maximum energy. And the unit has to be in million electron volts. And that's for betas, the average energy. And for gammas, it's monoenergetic, so there's no average. And finally, phi, the Greek letter phi, stands for the fraction of the energy absorbed in the target organ. Now, for betas, we make the assumption that that is 1, because any beta emitters that are absorbed or localized in an internal organ are going to give up all of their energy in that organ. Beta particles don't go anywhere. They go 2 or 3 or 4 millimeters, so they typically don't escape the organ. So here's what this equation looks like for betas. The beta dose is a constant times all of those factors. And if you use the right units, this is the proportionality constant. That's not too important. Here's the gamma dose, again, an almost identical equation. The difference here is that for betas, this factor phi was 1, and for gammas, it will never be 1. It'll be 0.1, 0.2, 0.4, maybe 0.5, somewhere in that range. So that number we have to put in. We can't assume it's any particular number. And again, that's the dose. Now, let's say that we wanted to calculate the total dose from 1 beta plus 1 gamma. Then if we did that, we would factor out what's constant And so we would have the fraction of betas times the energy plus the fraction of gammas times the energy times phi, all in brackets. And that's what the equation would look like for one beta plus one gamma. If there's more than one beta and more than one gamma, there would be a lot of terms here in the brackets. Now, that is a nice equation to look at, pretty easy to understand. We understand what all those factors are. I'm going to show you another equation that when you look at it, your first thought is going to be, it's all Greek to me because it's just full of Greek letters. But all I want you to do is understand the concept that's used here. This is done in computers. No human could ever do it. What a computer could do in 2 seconds could take you 100 hours. So let's take a look at this formidable looking equation, and here it is. It says that the total dose is going to be the activity over the mass times, this is capital sigma, it's a summation function. It's the sum of all contributions from non-penetrating radiations. Now, what would non-penetrating be? That would be alpha particles, beta plus particles, beta minus particles, internal conversion electrons, and Auger electrons. Those are all non-penetrating. And then we have all of the activity over mass times the sum of all contributions from the source organ to the target. And I'm going to explain that to you. It'll make a lot of sense in less than 1 minute. Source to target. For example, we know that sulfur colloid, when we eject it, goes to liver and spleen and bone marrow. Suppose we wanted to calculate the liver dose. Where is it coming from? It's coming from the spleen, from the liver itself, and from the bone marrow. So we have to consider all three sources for the one target. And we have chosen the target to be the liver. I'm going to just skip that because I don't think it's too necessary. And take a look at what this equation is telling you. The dose is going to be all the non-penetrating contributions plus the dose from the liver to itself plus the dose from the spleen to itself plus a term that I left out on purpose, which would be from the marrow to the liver. The reason I left it out is the marrow is not, it's in our pelvis. It's not very close to the liver, and only 5% of the sulfur colloid went to the bone marrow anyway. So that's going to be a negligible amount. We have left it out. Perfectly okay to put it in. So the point here is that we have to consider every source, liver and spleen and marrow, for the same target that we have chosen, which is the liver. Now, let's take a mental break before we take a look at a couple of units. Any questions about anything that we have covered on internal dosimetry? Anyone have a question? Okay, if not, let's take a look at a couple of units here. A sievert is 100 rems. I'm going to concentrate on sieverts because that's the dose for humans, not for other objects, but for humans. So our dose would be sieverts, and a sievert is 100 rems. Therefore, a millisievert is 100 millirems. That is, the ratio will always be 100. So if we take the number of rems divided by 100, we come up with the number of sieverts. Now, I think I asked you this earlier. Our MPD is 5 rems, and we said that's 5,000 millirems, and that's equivalent to 50 millisieverts. And if you want to see here, here's the math. Converted rems to millirems by multiplying by 1,000, and then converted millirems to millisieverts by dividing by 100, and there's our 50. Now, what about this? Patient study resulted in a whole body dose of 200 microsieverts. How many millirems is this? Now, that might look like a tough problem, but truly it's not at all, because first you're going to convert microsieverts to millisieverts. So 200 microsieverts is going to be 0.2 of a millisievert. And if we want to find millirems, we take 0.2 and multiply it by 100, and it comes out to be 20. Here's the math if you'd like to see it. We took the 200 microsieverts, multiplied it by, and we know that there's 100 microrems in a microsievert by definition. And then we convert the microrems to millirems. And there's your answer. Now, a patient was accidentally injected with the wrong radiopharmaceutical. You know that that's an event. An event is any happening where a patient got the wrong drug or by the wrong route or by the incorrect activity, not within plus or minus 20% of the prescribed dose. That's an event. This is asking you, is that a recordable event or a reportable event? And the only number I've given you is that the whole body dose is 60 millisieverts. So who knows? Is that recordable or reportable? Anyone?
Reportable.
Reportable?
Yeah.
Good. 60 millisieverts is 6,000 millirems. We simply multiply by 100, and we know that 5,000 millirems or higher is a reportable event. And so that definitely would be a reportable event. That's excellent. Now, I just want to mention, we covered this once before, and I want to briefly mention while we're on units, the conversion of millicuries to gigabecquerels. There are a couple of products we buy today. They're really mostly therapeutic. They come from other countries. The term millicurie is not even on the label. It will give you gigabecquerels or megabecquerels. How do you do the conversion? So you need to know the conversion factor, which is that 37 megabecquerels is 1 millicurie. We covered that in probably the second or third lecture. So here's the math. 3,000 millicuries times there are 37 megabecquerels per millicurie. That gives you 111,000. And a gigabecquerel, by definition, is 1,000 megabecquerels. And so 3,000 millicuries, which was 3 curies, is 111 gigabecquerels. Now, you'll recall when you bought your first computer and had a megabyte of disk space, and you were so proud of your megabyte computer, and 5 years later, it was a gigabyte computer. And now there are laptops that have a terabyte or more. A terabyte, that's a million megabytes, unbelievable amount of space. If you have a 1 terabyte computer, you could literally run a small country off of it. Now, one other term I want to mention, this has started to appear on board exams over the last, let's say 10 years, and that's called cumulative activity. And it's always measured in units shown on the bottom of the slide here. It's in terms of microcurie hours, and it really relates to the total disintegration over time. Here, this will probably help you. If you are a math major, this might make a little sense to you. That is, the activity, the total activity deposited over an infinite number of hours. That is, if we're integrating from time 0 out to however long it takes for all of it to decay, it would be the integral of activity as a function of time. And you're going to see that it comes out to be exactly the mean effective life, 1.443 times T effective. Well, let's see where that came from. If you integrate under the curve here, if you measure the area under this curve, this rectangle here has identically the same amount of area, this blue rectangle, as the area under the curve. And look where this rectangle falls out. 1.443 times the T effective. That's the mean effective life. And so this is giving you a sense of the microcurie hours, how long it took and how much activity decayed for the complete disappearance to take place. Now, just to give you, I'm going to do one simple calculation for you, and then I'm going to skip a couple of the other problems that are here because I don't think that they're important enough to spend time on. Let's say we gave a patient 5 millicuries of sulfur colloid, and the liver uptake was 85%. So 0.85 times 5 is about, 4 point something. And assuming that the biological half-life is infinitely long, and we know that's correct, sulfur colloid never clears the body. We humans can't ever get rid of it. And 100 years from now, when we die, it's still in our liver. Doesn't mean anything. It's not harmful at all. So let's take a look. The cumulative activity is simply going to be the activity starting activity A0 times the percent uptake. That would be the 5 millicuries times 0.85. This product is how much is in the liver. And we multiply it by 1.443 times 6 hours. And look what we come up with. 36,000, almost 37,000 microcurie hours. That's a really large cumulative activity. Now, by comparison, if we deal with xenon, take a look at the numbers here. We had 37,000. Look at this. The xenon is only 192 microcurie hours. And why is that? Because the T effective is very, very short. It's measured in seconds, not in hours or years, seconds. So this is the reason we have to give a lot of xenon for a ventilation study, because the number of microcurie hours is very small. So we have to give 30 millicuries compared to only 3 millicuries for a pulmonary perfusion scan. I'm going to skip all of that. And we covered this once before, common board question. What are the 3 principal sources of our background radiation? We live at sea level. We will expect to pick up about 300 to 350 millirems in a year, doing nothing but sitting in our office or staying home. It doesn't matter what you're doing. You're going to pick up those millirems. What are the 3 principal sources? And out of those 3, which is the principal source? So what are the 3? Who knows?
Naturally occurring things in our bodies.
Good. We are all radioactive. We have potassium-40, 1.3 billion year half-life, and we have carbon-14, 5,760 year half-life. So we're radioactive. That is not the most significant source at all. What are some of the other sources? 2 more.
Medical.
Sorry?
Medical examinations.
Definitely not. That is never considered part of your background. That's simply medical radiation. We're just talking about background. Let's say you sit in
Terrestrial?
Okay, terrestrial sources. And how about extraterrestrial? So here they are. We have cosmic rays. We can't get away from them. We're being bombarded with them right now. You can't feel them, of course. And they are so penetrating, they deposit very, very small amounts of energy. So we have cosmic rays. We have our radioactive bodies, but very, very low level activities with very long half-lives. And then we have terrestrial sources, minerals in the soil. There's radium in the soil that creates radon, and we don't want to breathe radon because when it decays in your lungs, it decays to polonium, and the metal is trapped in your lungs, and that actually is what causes, potentially causes lung cancer. It's really not the radium. Sorry, it's not the radon, it's the polonium daughter. Radon is in and out. Polonium is trapped in your lungs and can't get out at all. So radon is by far the biggest contributor to our background. And here's a chart that will show you that radon is the largest contributor. Is cosmic rays, internal, medical, other terrestrial things. We have consumer products like smoke detectors that contain americium-241. These are the minor sources. Contaminants in the food chain, essentially zero. Nuclear power plant emissions, essentially zero. Flying in airplanes, very, very low dose. You can fly from New York to London and back, and all you're picking up is the equivalent of 1 anterior chest film, perhaps 10 millirems. Now, what about people in Denver? People in Denver, these numbers are very old, by the way, and they're wrong. This top number at sea level, it should be about 300. This number at Denver is more like 600. And there are 3 places on Earth where the background is so high that people can pick up 7,000 millirems per year. One of them is in Iran, one of them is in India, and one of them is in Brazil. Now think about this. In 50 years, a person picks up 50 times 7, that's 350 rems. That's the LD50, that's a lethal dose where 50% of the people would die if it's an acute dose. But this is not an acute dose, it's a chronic dose. And very interestingly, the cancer rate in those 3 locations is no higher than anywhere else in the world. Now, excuse me. People who live in Denver have double the background dose that we have here at sea level. True or false? That's because Denver is 1 mile closer to the sun and they have lost the protection due to the inverse square law. True or false?
True.
So if you did the inverse square law, you would see that it actually, in that 1 mile, increases your dose by approximately 0.000001, about 1 millionth. What's 1 mile out of 93 million? We didn't move far away from the source. We're already, what's the difference between being 92.99999 million and 3 million? There's almost no difference whatsoever. So why do people have higher background rates in Denver? It's not because of proximity to the sun. It's for two reasons. Number one, there happens to be more radioactivity in the soil out there in the West. And number two, probably more importantly, Denver is called the Mile High City. You're, over 5,000 feet up in the air, and the air is thinner and less dense. And so down here in Chicago or wherever you happen to be, you have the attenuation of the densest mile of the Earth's atmosphere. But in Denver, it's basically under their feet and not over their heads. And so their background is pretty much double ours. Just this is sort of a fun slide, really. What is your risk of dying from 1 rem of radiation? They say it increases your chance of death by only 4 parts in 10,000. Now, if you take a look at this list, there's almost nothing here that you would be unwilling to do. And that's the point of the slide, that 1 rem of radiation is pretty risk-free. For example, living 2 years in New York, nobody would hesitate to do that. Traveling 40 hours by canoe. Now, the risk for all these things listed in the right-hand chart, but 40 hours by canoe, you're going to die from an accident, or flying 500,000 miles in a jet plane, or having 20 mammograms in your lifetime, or drinking Miami water for 400 years. I mean, there's no way to possibly do that. The bottom line here is that the risk of dying from 1 rem of cancer is essentially zero. It's probably even lower than 4 parts in 10,000. And finally, here's some radiographic procedure doses. Anterior chest film is very small, 10 millirems. Lateral is 42. Abdominal x-rays and lumbar spine, the dose goes up. CT scan, probably the highest dose thing we'll ever get today. The dose is 4 to 5 rems per exam. That's not a whole body dose. That's a target organ dose. For example, if you had a CT of the head, you get 4 to 5 rems to your head, but the whole body dose might be a couple of 100 millirems. Fluoroscopy, very high dose, 2 to 3 rems. That's 2 to 3,000 millirems per minute of fluoro time. So if you have what we like to call a lead-footed radiologist, you could get a significant dose. Okay, now we're going to take a short test on internal dosimetry, and then we're going to proceed to the next topic. Number one, Madame Curie's professor carried that glass vial with the radium in his coat pocket and had the first documented skin burn. What caused that skin burn? Was it caused by the approximately 5 million electron volt alpha particles, or by the gamma rays that accompanied that alpha decay, or Cherenkov radiation, or 0.005 keV X-rays? Who's got it? A, B, C, or D? Anyone? Okay, so let me pose another question to you. What are the chances that an alpha particle could escape that glass vial? And the chance is
Low.
extremely low. It's actually zero. An alpha particle can't go through 1 sheet of paper. How could it get through a 2 millimeter glass vial? It cannot be A. And in fact, the correct answer is B. It's the gamma rays that pose the risk and cause the burn. Cherenkov radiation, you would only find that in a reactor core, and an X.
Dr. Karish, you're muted.
It muted me. Can you still hear me now?
Yes, but we can't see your screen anymore.
You say that you can't see okay, let me see if I can share the screen.
Your screen.
Hold on 1 second. All right, can you see the screen now? I did.
Yeah.
Yes? You can see this
Yes.
slide? Yes, okay. I don't know how we lost the connection, but fortunately very brief. Okay, number 2, irradiation of the juvenile thyroid has been associated with an increased risk of developing what? A, B, C, or D?
A.
A. I'm
A.
sure A is correct. The Alara concept has contributed to which of the 4 following ones? A, B, C, or D?
B.
That would be B. Overall reduction in dose to radiation workers. Number 4, a radiation worker may receive a whole body dose of how many REMs? This is in a year.
C.
That would be C, 5 REMs, 5,000 millirems, 50 millisieverts. How about our families? What are they permitted?
0.1.
A.
A, 0.1, that's 0.1 rem, that's 100 millirems, that's 1 millisievert. Effects caused by ionizing radiation include all of the following except which one? That would be choice A. I didn't mention cataract induction at all, but cataracts have been caused by ionizing radiation. And in fact, a colleague of mine, a physicist, was working with a laser beam and accidentally looked into a live laser beam at the age of about 25. And within a year, he developed cataracts that had to be surgically removed. So the correct answer here is malignant melanoma is caused by ultraviolet radiation from the sun and not at all by ionizing radiation. Okay, there are 20 contributors to the internal radiation dose for technetium. All of those are in that list except which one? A, B, C, or D?
C.
B. Sorry, C. Beta
Yeah.
particles are not emitted by technetium ever. All the rest are. Number 8, the mathematical equation that we looked at earlier includes all of the following except which one? Let's go down the list. Fraction is included. Effective half-life included. The energy included. Size and shape of the organ, we don't account for that, not directly anyway. Okay, before we dive into personnel monitoring devices, are there any questions that anyone has about dosimetry? If not, then let's jump right in here. What's the purpose of measuring our occupational exposure? Well, of course, we want to be in compliance with federal law, but here are some of the reasons that we do it. It gives us information that helps us to identify what are often referred to as undesirable practices. And sometimes we can even find unexpected sources of high exposure. Let's say you are coasting along getting 20 or 30 millirems every month, and all of a sudden, 1 month you get 100. The RSO is going to come and find out what you did that caused that practice. So it helps to identify something going on. Now, the book I took this from said it permits prompt application of controls. That, in fact, in general, is the wrong word here. I don't like the word prompt. Think about this. You put a film badge on today, or a Luxel badge, you put it on today, and let's say you got a high dose today. Of course, you don't know it. When are you going to find out? Well, you're going to wear that badge for a month, and then the RSO is going to mail it to the company who processes it, and it could take up to 2 weeks. So it could take anywhere from 2 weeks to 6 weeks to know what your dose was. So prompt is not really a very good word there. Also, it gives us information so that we can compare with our long-term limits set by the NRC, like the 5 REMs. And finally, it will help us to reduce our exposure by determining what activities are going on that's causing that higher reading. Here's right out of the NRC regulations. Who has to be monitored? You have to monitor any individual where it's likely that that person is going to pick up more than 10% of the MPD. That means 500 milligrams in a year. I'll give you an example. We had a doctor who came from Greece over to Loyola and spent 6 months in our department. In my boss's good medical judgment, it was likely that this guy could pick up 500 milligrams. He was standing by patients all the time. He was in the hot lab learning how to elute the generator and make kits and draw doses and inject doses. And we didn't want to take a chance. So we monitored him. And so personnel monitoring is not required when the nature of the job is such that it's very unlikely there's going to be an exposure of any kind. For example, aside from people like secretaries and other administrative people, occasional visitors, messengers, servicemen, delivery men, they do not have to be monitored. Now, if their company wants to monitor them, that's fine. But if we are the recipient of packages, we have no obligation whatsoever to put a monitor on any of those people. That's their employer's responsibility if they choose to. Long-term visitors, we just have to make sure that they stay under 0.5 REMS. Now, the ideal device has to meet certain requirements. Number one, it has to accurately measure the dose received by the parts of the body that are most likely to be at risk. And that would be, there are 3 of those. The bone marrow, we don't want to cause aplastic anemia or leukemia. The gonads, we don't want to cause genetic defects. And one which is not listed here is the lens of the eye, and that's the 3rd of the 3 most vital tissues. So, I see people wearing their film badges in the wrong place. You may have seen people wearing it up on their collar. Last time I looked, nobody's bone marrow is up there. Your bone marrow is in your pelvis. It's not up there. So wearing it up there is not doing any good. It's not assessing anything directly related to gonadal or bone marrow dose. And that's number one. We want to put it in the right place. We want to measure the dose to those critical organs. And number two, the measurement has to be totally independent of whether it's alpha, beta, gamma, whether it's low energy or medium energy or high energy. It has to be able to deal with all of those. And mentioned earlier, the records have to be preserved forever until the NRC tells you can shut down your license. I'm going to skip that slide. What would you consider a reportable exposure record? If a reading is way too high, if it's a whole body reading, could be reportable. A finger or a hand reading could be reportable. Measurements, internal measurements, though, let's say that you might be contaminated. Somebody did a whole body scan on you to see if you have internal dose, and all of those could be reportable exposure records depending upon how high those doses are. Who has to be given exposure records? Number one, occupationally exposed workers, that's all of us, on an annual basis. Number two, if you move to a new job and you petition your former employer, they have to furnish it to you and the new RSO within 30 days. When we have our little quiz in a while, I'm going to ask you a question about this slide. And also, if there is an overexposure, that has to be reported to the NRC, or if you're in an agreement state, the state regulators within 30 days. Now, here's a very important concept to nail down. Personnel monitoring devices are called integrating. That means that they are measuring doses over time. We wear a film badge over time. What's not an integrating measurement would be something like a Geiger counter. If I put a Geiger counter to your chest and take a reading, that's telling me what the dose rate is at that moment in time. It's telling me nothing about your absorbed dose at all. So these devices are collecting radiation over time. They're integrating devices, unlike survey meters or those kinds of things. All they give is an instantaneous readout. more important things here. The device has to be compact and light, and you all know they weigh so little, you can't even tell you're wearing it. You can't feel it at all. Also, they have to be relatively inexpensive. Remember, some institutions have 100 workers that they have to badge, and they have to pay for, let's say, um, if it costs $25 per month, you're looking for 100 workers, you're looking at $2,500 per month times 12 months. You're looking at $30,000 to monitor people. And some really big institutions have even more than that. So we want them to be inexpensive. I actually don't think they're $25 a month. I think they're still a little bit lower than that, but they have to be changed every month. And remember, there are film badges, ring badges, and film badges for our bodies. They have to be reliable, accurate, sensitive to the kind of radiation, inexpensive, portable. How important is it to understand the operation of your monitoring device? The real answer to that is it's zero. It's not important at all. You need to know because you're taking an exam. They might ask you how it works, but for the typical wearer who doesn't understand how it works, nobody cares. All we care about is, did you turn it in at the end of the 30 days? Now, this is what a film badge looks like. And the film badge used to be the most popular type of monitoring device until probably 7 or 8 years ago when Luxel badges became available. We're going to talk about that shortly. But a film badge has a photographic emulsion. It's a small piece of film, and it's overwrapped in plastic to keep it waterproof, and then overwrapped again in black light tight paper. Visible light would just overexpose it. And that is able to measure your whole body exposure and also distinguish the type of radiation. How can it do that? Film badge has these cutaways, and there are 3 different metals in there. One of them is copper, which is really pretty dense, not as dense as lead, but pretty dense. We have cadmium, medium density, and aluminum, very low density. And so because they attenuate at different rates, they're able to distinguish whether one is exposed to high energy or medium or low. Film badges, in that film, there's silver halide, that's silver bromide or silver iodide. Those are the ones that they use. And when exposed, when the film is developed, that latent image forms and it's reduced to silver metal, and that's what makes the little black dots on the film. And then we use a device called an optical densitometer. Now, the human eye is pretty good at shades of gray. Maybe we can tell 25 or 50 or 100 shades of gray. An optical densitometer can distinguish 1,000,000 shades of gray, and our eyes are simply not able to do that. So we will use the optical densitometer and compare our reading to a standard reading, and then we can tell exactly how much the dose was. So those metal filters are valuable only for the photographic emulsions. The advantages of film badge, they're permanent records. You can go back and reread that film 10 years later. They don't cost you much, 10, 15 bucks. You don't need technical knowledge. The downside, it takes weeks to get the results typically, and they're not very sensitive or very accurate at low levels. Like if you were to pick up 4 or 5 millirems, it might read 4 or 5 and it might read 6 or 8. They're not that accurate on those very low levels, but above 40 millirems, they're pretty good. Reproducibility is okay, but not spectacular. Also, don't ever leave your film badge on the dashboard or the sun visor of your car because sunlight will ruin it. And don't ever put it in the washing machine by mistake. If you do so, you have 2 choices. You can lie to the RSO and say, I lost my film badge, or you can tell them the truth and say, I washed it in the washing machine. Either way, it's going to give a totally abnormal reading. And for that month, the recording will be pretty useless. Also, film badges need to be turned in pretty quickly because the image does change as a function of time. You don't want to turn it in a year later. If it's a month late, okay, but you want to turn it in at the end of your month. Now, what has largely replaced those film badges are what we call Luxel dosimeters. More than 80% of all hospitals in the United States use Luxel. And RSOs like it because they're very stable, very sensitive, very precise. And this is using something called optically stimulated luminescence, that's OSL. Here's how it works. Inside the little packet, there's aluminum oxide. When aluminum oxide is exposed to radiation, electrons are bumped up to higher orbitals and they stay there. When those badges are irradiated with a certain wavelength of light, the electrons release their energy in the form of visible light. They drop back to normal. And we have one shot at measuring that visible light and comparing it to standards. And you'll see conceptually, we're going to do the same thing with TLDs, thermoluminescent dosimeters, except that instead of optical stimulation, we're going to have heat stimulation. I just took this from the Luxel website. There's aluminum oxide in it. OSL is what's being used. The energies detected for photons are from 5 keV up to 40 million electron volts. We never use anything over 0.14 of, about 0.365 of an MeV. And even for nuclear and also beta particles, you can go up to 10 MeV. And look at the dose range here. This is from 1 millirem to 1,000 millirem. That's very wide range, a factor of 1,000. And here it goes from 10 millirem to 1,000. You don't need to know these numbers, but you should know that this contains aluminum oxide and it's OSL. And this is what a Luxel badge looks like on the right-hand side. Now, these dosimeters are very durable. They're not affected by anything, heat, moisture, pressure, and they can be used for up to a year. Next is a TLD, a thermoluminescent dosimeter. These are ring badges. They're only for people who are either working in the hot lab, where they're eluting generators and preparing and drawing kits and drawing doses, or the people who work in fluoroscopy wear them sometimes. Actually, many of them don't wear them because they don't want to register a high hand dose, but that's their choice, I suppose. And so the TLD uses thermo, that's heat. That heat takes those bumped up electrons, lets them come back to their normal level, releases light. That light is measured, and this process can be repeated many times. So the ring badge that you received this month, somebody else wore last month. And what really happens to them is they don't wear out. People just lose them. That's mostly what happens. And so instead of reading optical density, we are reading the visible light coming out, and it's compared to what's called a glow curve. And this is not done by us, but by a company that specializes in this. What's in the TLD is lithium fluoride. Lithium fluoride was chosen because it happens to be a molecule where the electrons are easily bumped up to higher orbitals and they stay there. I'm going to skip that, not important. And the very last thing before we take a quiz is pocket dosimeters. Actually, I love pocket dosimeters because they are really useful in giving you an answer right away. How much did I get today? Let's say you're going to visit a Central Radio Pharmacy on a tour. You're going to be there for 4 hours. You put one of these pocket dosimeters on. First, you take the reading. Say the reading might be 1 MR per 1 MR. Then you wear it for 4 hours. And then you take another reading, and now it's up to 5. So you picked up 4 MR in 4 hours. You know immediately what your reading is. Now, these devices can vibrate. They can emit sound. They can emit light. And all the modern ones, these three here, all have digital readings. In the good old days, going back 15 years or earlier, this is what a pocket dosimeter looked like. Excuse me. You can see the guy here on the bottom. He is looking through one end of the dosimeter, and there's a little grid there. And here is what he's seeing. He's looking at this grid, and if you see this little line right here, he's saying, okay, I'm getting ready to wear this dosimeter. My reading right now is 27. puts it on, wears it for a few hours, looks through the dosimeter again, and says, okay, my reading is now 37. I picked up 10 millirems during my visit. That's the nice thing about a pocket dosimeter. RSOs don't use them because if you lose a film badge, you've lost $10. If you lose a pocket dosimeter, you've lost a couple of $100, maybe more. And so because of loss, it's just not practical to distribute pocket dosimeters to everybody. The advantages, they're reusable, they're easy to read, and you have, here's the most important one, you have an immediate reading of your cumulative exposure. They are, of course, much more expensive and very fragile. Okay, conclusions. There are 4 different types of devices for measuring both instantaneous dose, only one really, pocket dosimeters, and the cumulative radiation dose. They all do that. Each one has specific applications. Some are for your hands, some are for your whole body, and each has its own advantages and disadvantages. Okay, before we take our test, any question from anyone about personal monitoring devices? Oh, okay, here we go. Now, one of the first things I told you in the very first lecture is read all possible answers. Even if you know choice 1 is correct, don't just quit there reading. So let's take a look. The question says, the purpose of measuring occupational exposures is to A or B or C, or A and C only, or all of the above. So let's read A, B, and C and tell me what you think. Who's got it?
All of the above.
Definitely all of the above. Exactly the right answer. Number 2, who has to be exposed? Who has to be monitored? Anyone who in your good medical judgment is likely to receive more than X%. What is X?
10%.
Good, 10%. In fact, your answer for any percent question other than prescribed dose, administered dose will be 10%. All your dose calibrator tests, plus or minus 10%. Which of the following occasional visitors to an institution must be badged? Messengers, servicemen, delivery men, all of them, or none of them?
None of them.
None of them.
None of the above. Good. Long-term visitors should be considered as occupationally exposed persons, meaning they need to be badged if it's likely that they will pick up more than X millirems in a year.
B.
Which one?
B.
B.
0.5.
0.5, sure. Remember, it's going to be 10% of the 5. So that's where the 0.5 came from. Good. The ideal personnel monitoring device is used to measure the most critical organ dose in the body. What would that be? A, B, C, D, or E?
A.
A, sure. Bone marrow and gonadal dose, that is by far more critical than everything else. Measurement of internal dose must be independent of which one? A or B or both or neither?
C, A, and B.
That would be C, A and B, sure. It has to be independent of the type of radiation. Remember we said it could be alpha, beta, gamma. We have to handle all of it. And the energy, it has to be able to handle low, medium, and high energy. Good, A and B. Personnel monitoring records have to be preserved for how long?
E. E.
E, until the NRC authorizes disposition. Number 8, reportable exposure could include and that would be all of the
All the
above.
above.
Sure, all of the, sure. If you have a whole body reading that's too high, reportable. Fingers too high, parts of the body, all could be reportable depending on what the limit is. Exposure record must be furnished to which one of the following. Now let's go down the list here because the timing on some of these is just wrong. Any currently employed occupational worker who requests it on a quarterly basis. Okay, that is wrong. What basis did we say?
Annual.
Annual, that's wrong. Anyone who requests it within 24 hours. That's wrong. 30 days. If you are taking a new job, the RSO has 30 days to, at the original job, to send the report to the new RSO. The individual and the NRC, in the case of an overexposure, 30 days. That is the correct answer. If you send your friend to the RSO and request a report, the RSO can't give it to your friend. And only another RSO, you can only give it to another RSO. Number 10. Personnel monitoring devices are A, designed to measure cumulative exposure and internal dose over time. B, are integrating devices. C, produce an instantaneous readout. A and B only, or all of those? Anybody?
A and B only?
A and B only, sure. We know that we know that it's giving us a cumulative dose. It's integrating over time. That's what this is, integrating device. So A and B only. We don't want an instantaneous readout. That tells you zero about a cumulative dose. Which of the following is not a consideration in the use of film badges? Okay, now that should be pretty obvious. You might like a film badge that matches your shirt or your dress today, but color is totally unimportant. Which of the following are false? Let's go down the list. Film badges are excellent for monitoring extremity exposure, like your hands. True or false?
True. True?
I don't-
No?
What do you wear when you want to monitor your hand dose?
TLD.
Yeah.
Sure, right. You wear a TLD or a ring badge. So film badges, you have no way to hook them to your fingers. So that's false. Film badges are good for whole body exposure. That is true. So the only one which is false would be choice A. Which two of the following are false? Let's go down the list. Film badges are the most popular type of monitoring device today.
False.
That is false. They used to be, but not anymore. Film badges contain lithium fluoride chip and are TLDs.
False.
False for every reason. There's no chip in it. There's no thermoluminescence. Film badges contain photographic emulsion wrapped in plastic, overwrapped in light-tied paper. That is true. Film badges are designed to measure whole body exposure. That is true. They're able to distinguish type of radiation. That is true. So A and B are false. Film badges can distinguish among different energy photons because they contain special circuitry, they contain metallic filters, they contain lithium fluoride chips, or they only absorb low energy photons.
B.
B.
Sure. There are metallic filters of low, medium, and high density, and that's what helps to differentiate the energies. Number 15, how do companies determine our exposure from a film badge? The right answer is B. They use an optical densitometer. The glow curve is only used for TLDs, and you certainly don't weigh the film before and after. So B is the correct answer. 16, which of the following is false? Let's go down the list. The film badges provide a permanent record. That's true. Inexpensive. That's true. Require no technical knowledge. That's true. They're sensitive down to around 3 MR per hour. That's true. It takes weeks to obtain, I'll go back to the previous one. They're not very good down at the 3 MR per hour level. That they're not sensitive down there. They're good at 30 or 50 or 100. It takes weeks to obtain the result. That's true. So the false one is this one, sensitive to 3 MR. 17, TLD ring badges are important for eluting generators, injecting patients, and so on. Which one of these is true? Let's go down the list. TLD dosimeters contain lanthanum fluoride. That's false. It's lithium fluoride. TLDs trap excited protons. That's false. They trap excited electrons. TLDs are used one time and discarded. That's false. They're reused until people lose them many, many times. The TLD is heated and the amount of light emitted is compared to a glow curve. That is the correct answer. That one is true. And TLDs are unreliable above 1,000 millirems. They go up to many, many rems. So the only one of these that's true is the one about the light emitted and the glow curve. Which of the following dosimeter statements regarding pocket dosimeters is true? We'll go down the list. They're useful in situations where you could get a large exposure in a short period of time. That is true. Use a glow curve, totally false. It's an integrating device, totally true. You're integrating over time. A and C, and therefore D would be the correct answer. We're almost done. Which of the following for pocket dosimeters is true? Compared to a TLD, a pocket dosimeter is fragile. Very true. It gives you both instantaneous and integrated reading. That's false. It only gives you an integrated reading, not instantaneous. Pocket dosimeter is more expensive than a film badge. Very true. And so the only one that is true here is, A is true. Oh, it says is are true. Yes. So A and C, and therefore D is the correct answer. Number 20, you visited a central radio pharmacy for a visit 4 hours. What would you want to wear to monitor your dose?
D.
D.
D, 100%. You want a pocket dosimeter. Before you walk out of that lab, you will know what your absorbed dose was. Okay, we are now actually finished with all of the former lectures. And before we do a quick review of the requested topic I did get from one person in the group, let me pose the following offer to you. Do you have any question from about anything we have covered in any of these 10 or 11 lectures? Any questions about anything? Is there anything you would like me to review with you for the rest of this class? Next week, we're going to do the math review. So my expectation is that you will have completed math test number 1, math test number 2. Those are both with links onto the website. And then the third math test should have been distributed to you by your program director. And it's either a PDF or a Word file, but I think it has like 20 or 25 questions on it. We're going to try to get through all of those next class. So any topics you would like reviewed today? Anyone? Okay, in that case, give me a moment, please, to find the requested topic, which was pretty close. Okay, so the request that I got, sorry, hold on. Let me start the screen sharing again. Okay, I assume you can see that slide on the screen that says shielding formula?
Yes.
Okay, so we're going to do a quick review of the shielding formula. As we go through this, I might skip a slide or two because mostly I want you to make sure you understand the difference between a half value layer and a 10th value layer. I don't think the math is so tough really, but the concept is a little hard. So just as a very fast review, as I mentioned the first time we went through this, attenuation is exponential. You'll recall that it is not linear. It doesn't go from 100 to 50 to 0. It goes from 100 to 50 to 25 to 12.5, just like decay. So we are dealing with what we call the half value layer. That thickness varies all over the place depending on whether the absorber is lead or aluminum or paper or whatever. So the half value layer is defined as the thickness of an absorber that will reduce the beam intensity to 1/2 of its original value. And once you know how many half value layers you've got, all you care about is N. What's the number of half value layers? Just like when you work a decay problem, all you care about is N. How many half-lives have elapsed? That's all you care about. You don't care what the isotope is anymore once you know how many half-lives have gone by. The formulas don't care at all what the isotope is. It's just totally irrelevant. So once you know how many half value layers there are, you just don't care. Which stops more technetium energy, a half value layer of lead or aluminum? Anyone?
It's the same.
Who's got it? Remember,
It's the same.
lead is very dense, aluminum is very light, but which one stops more?
The same thing.
They're the same. A half value layer is a half value layer. We don't care what it's made out of. Once you know N, the number, we don't care. It's one half value layer of feathers and a half value layer of lead. They're both going to stop the same amount. And here's what we've got. We have a source, a monochromatic source, which we'll define as monoenergetic, going through a bunch of barriers. They're identical in composition and thickness, and reaching a detector. And so I'm going to show you this graph here. This is showing you that from the 0 point, we're right here. As we add in half value layers, the first one cuts it in half. The second one cuts it to a 1/4, to an 1/8, to a 16th, to a 32nd. And as we take layers out, we're going to double it, and then quadruple it and octuple it times 16 times 32. Now, I'm going to skip that. I do want to mention this. The mu is the linear absorption coefficient. And just like lambda, you'll recall for decay, lambda is 0.693 over T1/2, where T1/2 equals the half-life. Here, T1/2 is the half thickness, but we prefer to call it the half value layer. So the mu, the linear absorption coefficient, is 0.693 over HVL. Now, I'm going to skip that. You'll recall that we said that simply the fraction remaining, and this has to do with attenuation, radiation, and decay. The fraction remaining or penetrating is simply 1/2 to the power of N. If you're doing a decay equation, you're going to use this. If you're doing attenuation, you're still going to use this. This is a fraction penetrating. And so here's your formula. You take the original intensity and multiply it by 1/2 to the power of N. And that gives you the final intensity. Concept's very simple, where you're simply multiplying 1/2 by itself N times. And so here's your formula. If you have N is actually the thickness divided by the HVL. For example, my computer desk here is 4 centimeters thick, but the half value layer of this wood for technetium is 1 centimeter. I've got 4 half value layers. I took the thickness divided by HVL. This formula will work for all half value layer problems, all of them. And let's compare a half value layer to a 10th value layer. Now keep in mind, here's what that half value layer did. It went from the initial beam intensity to a 1/2, to a 1/4, an 1/8, a 16th, a 32nd, 64th, 1/128, 1/256, 1/512, and 1/1024. That means that 10 half value layers reduced it by a factor of roughly 1,000. It went from 1 to 1/1024. A TVL is different only because it's thicker and it's going to reduce the beam intensity much, much quicker. Now, look at the definition. The thickness, TVL is that thickness of an absorber that reduced the intensity to, not by, but to 10% of its original value. So it went from 100% to 10%, to 1%, to 0.1%, to 0.01%. Just keep dividing by 10. Or to look at it another way, it's going to go from 1,000 to 100 to 10 to 1 to 0.1 to 0.01 to 0.001 ad infinitum. So while a half value layer reduces the beam to 1/2 of its initial value, this is 1/10. And so the equation is going to look like this. The final reading will be the initial reading times 0.1 to the power of n, the number of 10th value layers. And so all TVL problems can be solved with that equation. Just have to remember that the half value layer, it was I0 times 0.5 to the power of thickness over HVL. And here it's 0.1 to the power of thickness over TVL. These two have to be consistent. If this is 0.1, this has to be 1/10. Let me see if anything I wanted to cover. Yeah, let's take a look at this. So here, you can go from your original value to, as you put TVLs in place, it's going to drop by a factor of 10, then by a factor of 100, and then 1,000, 10,000, 100,000. And as you take out TVLs, it's going to go up. First TVL you take out goes up by a factor of 10, then it goes up by a factor of 100, 1,000, 10,000, 100,000. Okay, now let's look at the bottom line on this slide. Which stops more technetium energy? A half value layer of lead, more dense, or a TVL of aluminum, much less dense?
The TVL.
Of course it does. How about the first one? Which stops more, a TVL of lead or a TVL of aluminum?
Are those the same?
They're going to be the same. A TVL is a TVL. Remember, once you know this number 1, you don't care what it's made out of. It's unimportant. A TVL is a TVL. Doesn't matter if it's lead, aluminum, wood, feathers, it does not matter. But here, a TVL of anything will stop more than an HVL of anything, because this is knocking it down from 100% to 10. This is knocking it down from 100% to 50. So that, in this case, a TVL of anything will stop more than an HVL of anything else, anything different. Okay, let's jump ahead a little bit. Actually, I want to ask you a question about this. When I asked you the first time several weeks ago, no one got the answer right. So let's see if you remember it now. You'll see as you go through 1, 2, 3, and 4 layers, the half value layer goes from 1,500 to 250, 125, 62.5. But the TVL goes from 1,000 to 100 to 10 to 1 to 0.1. And therefore, 4 TVLs is how many times as effective as 4 HVLs? Who's got it?
625, is it?
What did you say?
625.
Perfect. 625. Remember, 4 TVLs reduced it to 0.1. 4 HVLs only reduced it to 62.5. So if you take this divided by 0.1, that ratio is 625 to 1. So 4 TVLs is 625 times as good at stopping radiation as 4 HVLs. Now, we worked, let me jump ahead. We worked these 6 problems last time, and I think you did pretty well, but let's take one last look at them. We have 4 HVLs in place. They're equal in thickness because they're all the same absorber, and this is a monochromatic beam. And with the 4 in place, we have a reading of 100. Now, if we take out 2, we took out this N1 and this N1. If we take those out, the reading is now what? Is it going to go up or down? And to what number? I think
Go up.
it has to go up. You took out 2 layers. What's this number now? You took out 2 layers, 2 half-value layers. What's this number right here? Anybody? All right, when you take 1 half-value layer, what happens to this reading? It goes from 100 to,
150?
no. What do we say a half, what does it do? Half-value layer. It either doubles it or halves it, correct? So
That
it's,
would take it up to 1,000.
no, we're talking about half-value layers, not 10th-value layers.
We'll take it to 400.
The correct answer is 400. Look, it's at 100. When you take the first layer out, that doubles it to 200. You take the next layer out, it doubles it again to 400. Okay, All right. Is that clear before I leave the slide? Everybody
Yes.
following? Every time you take a layer out, it's going to double it. So if we're doubling it twice, it's going from 100 to 200 to 400. And there is your answer, 400. How about if we take out a third one?
800.
800.
Good. It went from 100 to 200 to 400 to 800. Now, how about the reverse? We had 4. Let's put in 2 more. Now, you know the reading is going to go down. We put in 2 more half-value layers. The reading is going to go down. What does it go down to?
Would it be 25?
Good. It's going to go from 100. One layer takes it to 50. The next layer takes it to 25. It's 1/2 to the end. 0.5 to the power of 2 is 0.25 times 100 is 25. There it is. Now, I'm going to give you the same 3 problems, but here we're going to deal with TVLs. And I think people seem to have more trouble with TVLs than half-value layers, but it's not hard. You just keep dividing by 10 or multiplying by 10. With HVLs, you either kept multiplying or dividing by 2. So here, we have 4 TVLs in place. The reading is 100. If we take out 2 of them, what's the reading now?
Is it 1?
10,000.
Oh, 10,000. I don't know.
Yes, you do know. You do know, yes. We're taking them out. That means the reading's got to go up. What's it going to go up to?
10,000.
10,000.
10,000.
Good. 10,000, sure. It's going to go from 100 to 1,000 to 10,000. There's your answer. How about this? Let's take out another one. We took out 2 and it's 10,000. Let's take out another one. Now what's it going up to?
100,000.
100,000. Going to just multiply by 10 again. There it is. Great. Now let's add 2. We had 4 TVLs. Reading was 100. We added 2 more. Reading is going to go down, right? We put in 2 more layers. Got to go down. What's it going down to?
This one's 1.
1.
Right? It's going to go from 100 to 10 to 1 to 0.1 to 0.01. Okay. Now, hopefully that gives you a better understanding of HVLs and TVLs. I did skip some of it. Maybe we'll take a quick look at a couple of math problems. And then I think there were a couple of other topics that someone expressed interest in. Everybody feel pretty comfortable now with HVL and TVL? Hope that clarified it for you a little bit. Now, here's an interesting problem. And this came right off an old exam. You cannot come up with the final answer without a calculator, but you can get up to the final stage by working it in your head. Here are 2 metals bonded together. This one is 2 centimeters thick, and this is 3 centimeters thick. For this 2 centimeter thick one, the HVL is 0.5. How many HVLs are there in that absorber?
4.
There are 4, right? 2 centimeters thick divided by 0.5. This is 4 layers. Keep that in mind. Okay, how about this one? We have 3 centimeters thick. The HVL is 0.75. How many layers is that?
4.
4. So how many layers do we have altogether?
8.
8. Now that you know n equals 8, this whole diagram is irrelevant. Your answer is going to be 1/2 to the power of 8. If you have your calculator, punch in 0.5 y to the x key 8. Here it is right here. We have 4 layers. 4 layers is 8. 1/2 to the power of 8 equals 0.00391. That's the fraction, but I didn't ask you the fraction, I asked you the percent. So 0.00391 would be 0.391%. Or if you count this on your fingers, you know, 1/2, 1/4, 1/8, 16th, 32nd, you come up with 1/256. Those three are all correct answers. Okay. Now, all of that had to do with a monochromatic beam. But you'll recall when we studied this the first time that we talked about polychromatic beam. And what did we say? The first half value layer, by definition, cuts the beam in half. But what can we say about the subsequent layers? What can we say about layer 2? Is it going to be thicker than one or thinner than one or the same?
Thicker.
Got to be thicker. And why? Because what did this first layer get rid of mostly? Low energy or medium or high?
Low.
Low.
Right. I showed you this big diagram here. And you'll recall we started out with 4 highs, 4 mediums, 4 lows, and the ratio was 4 to 4 to 4. And then when we put the first layer in, it got rid of half the total energy, but look what it did. It got rid of 2 of the 4 lows, 1 of the 4 mediums, and 1/4 of 1 of the highs. The second layer got rid of more low, more medium, and 1 full bar of high, and so on. Now look what happened after the third layer. When you reach the 4th layer, the low energy is gone, the medium energy is gone, and what's left over? Only the highest energy. So after 4 layers, this behaves monochromatically, and then it's going to go from 2 bars to 1 bar to 1/2 of a bar. It's hidden on my screen because I see your images here. Let's go back one, and here, this is what this is showing. You have a thinner one getting thicker and thicker and thicker. But now that we got to 4 layers, layer 5 equals layer 6 equals layer 7 equals layer 8, and so on. So after 4 layers, it's considered to be monochromatic. Okay. Let's see what you do with this. This was a good exam question. By definition, a half value layer reduces the intensity of the beam to 1/2 of the original value, and a TVL reduces it to 1/10 of the original value. That's a ratio of 5 to 1, 50% to 10. That's 5 to 1. That means a TVL is 5 times as good as an HVL. So look what the true false question says. We know a TVL is 5 times as good as stopping it, but true or false, a TVL is 5 times as thick as an HVL. True or false?
False.
Good. That's one of those things that's not logical because we humans like to do linear extrapolations, but this is a logarithmic function and linear just does not work here. In fact, take a look at mu. Remember we said the linear absorption coefficient is 0.693 over HVL. 0.693 happens to be the natural log of 2. So we could say mu is the natural log of 2 over HVL, which is equal to the natural log of 10, excuse me, over TVL. And that, if you punch this on your calculator, the ratio of TVL to HVL is the log of 10 over the log of 2. Not 10 over 2, but the log of 10 over the log of 2. And so while the TVL is 5 times as effective, it's only 3.3 times as thick. And that's because this is a logarithmic function and not linear. Now, if it's a monochromatic beam, whether it's HVLs or TVLs, they're irrelevant. You're going to get on log paper, you're going to get a straight line. But polychromatic, no matter what it is, TVL or HVL, you're going to get a curve. So we tend to read polychromatic beams off of curves. Very difficult to do mathematics. Let's see if there's any problems here that are really worth. Yeah, let's take a look at this one. If the TVL is 0.3 and the thickness is 1.2, what fraction of the beam can penetrate the absorber? Now, how many TVLs is that? The thickness is 1.2. The TVL is 0.3. How many TVLs is that?
15.
4. Good. That's 4 TVLs. What fraction can penetrate? 1/10 to the power of 4. Simply going to punch in on your calculator 0.1 y to the x key 4, and it's going to give you 0.0001, which is 1 times 10 to the minus 4, or 1 over 10,000. All those are totally correct answers. So you could calculate that on your fingers, actually, going from all of it to a 10th, to 100th, to 1,000th, to a 10,000th. You don't even need the calculator. Let's see. Yeah, here's a pattern recognition problem. A source has a reading of 4 MR per hour. Barrier is 4 centimeters thick. And the reading drops from 4 to 0.4. What is the TVL of that absorber? Here's a hint. You do not need a calculator at all. Who's got it? All right. The reading dropped from 4 to 0.4. What factor is that? It dropped by a factor of
10.
10. So if it dropped by a factor of 10, how many TVLs would 4 centimeters have to be?
4.
No.
No.
One. If it dropped from 4 to 0.4, by definition, that is 1 TVL. It dropped by a factor of 10. But how thick is it? 4 centimeters. So 4 centimeters is the correct answer. The TVL is 4 centimeters. This is pattern recognition. So sorry. If the reading goes from 4 to 0.4, that's a drop by a factor of 10. That must be 1 TVL. And here's the thickness, 4 centimeters. You can work it out mathematically, totally not necessary. Okay, inverse square law. We can touch on that for a couple of minutes also. Just to refresh your memory, it says the intensity of a point source varies inversely with the square of the distance. Now, what the beauty of this formula is, it's so easy to remember because when you cross multiply, look what you've got. I1 times D1 squared equals I2 times D2 squared. That's this. I1 times D1 squared is I2 times D2 squared. And that makes the formula very easy to remember. When I see a problem like this, I'll say, okay, this is I1, this is D1. I'm going to say 100 times 1 squared is equal to I2 times D2 squared. There's my setup right there, just by looking at it, and I know what the formula is. Let's see. Okay, let's work this one in our heads. We have a reading of 287 at a distance of 1.5 centimeters. If we move from 1.5 to 15, we're 10 times as far away. Is the reading going to go up or down? We moved 10 times as far away. Is the reading going to go up?
Goes down.
Reading is going to go down. If you have a reading of 287 at 1 centimeter, and then you take your detection device and move it away to 15 centimeters, the reading is going to go down. It's a point source. It's spreading out in every direction. And so if it went from 1.5 to 15, it's 10 times as far away. 10 squared is 100. We divide 287 by 100, and your answer is going to be 2.87. And anyway, you didn't have to do that in your head. You could simply say 287 times 1.5 squared is I2 times 15 squared. If you solve for I2 is going to be this times 1.5 squared divided by 15 squared, and you must punch equals at the end. Let's see, how about this one? I have a reading of 100 at 1 centimeter. We move from 1 centimeter to 1 millimeter. We are 10 times as close. That reading is going to go up by a factor of what? Remember, it's a square relationship. It's going to go up by a factor of 10 squared. And so the answer should be 10,000. Let's take a look at the solution. We have 100 times 1 squared is equal to I2 times 0.1 squared. Remember, this is 0.1 of a centimeter. These units have to be the same. If you mix them up, you're guaranteed failure. So this is 100 times 1 squared. It's I2 times 0.1 squared. Or you could say this is 100 times 10 millimeters squared. Is I2 times 1 millimeter squared. It's all the same. So this will be, I2 will be 100 times 1 squared divided by 0.1 squared. And that will give you 10,000. Okay, now I saw some puzzled looks on faces. Is that okay? So let me give you one more little mental exercise to think about. As we, if we start here, let me just go back to this diagram. Let's say we're right here at the point source. At whatever this distance is, there's your point source. At 1 meter, we have a reading of 40. Look what happened to the reading when we went to 2 meters. We doubled the distance, and what happened to the reading? It didn't drop by 2, it dropped by 4 because it's a square relationship. So it dropped by 4. The total energy has not changed. Here we had 40 units, here we had 40 units, but these 40 units are spread over a much larger area. So the energy density went down by a factor of 4 to 10. So now let's think about this. As let's say we're at one distance unit, let's say 1 meter. As we go from 1 meter to 2 to 3 to 4 to 5 to 6 to 7 to 8 to 9 to 10, here's what happens to the reading. As it goes from 1 to 2, it's a 4th. 1 to 3, it's 1/9. 1 to 4, it's a 16th. 1 to 5, it's a 25th. 1 to 8, it's a 64th. 1 to 10, it's going to be 1/100th. It's an inverse and square relationship. See if there's anything else there. Okay, I think that's all I want to say about that. Any clarification anyone needs on any of what we just covered? Anybody? Please don't be bashful. Please, if you have a question, just shout out your question. Anyone? Okay, then let's go back. This is going to give you a blur for a minute here, but let's just go back. Sorry, too far. Okay, and let's do a very fast concept review of radioactive decay. The concepts are just like what we just covered. Fortunately, there's no such thing as a 10th life, but there certainly is a half-life. So as you know, as we go through half-lives, we go from a half of it to a 4th of it, to an 1/8, to a 16th, to a 32nd. And you saw this graph before, it's identical. As we go through half-lives, we're cutting it in half sequentially. As we're going backward retrospectively in time, we double it, quadruple it, octuple it, and so on. Now, the best way to plot decay is on logarithmic paper like this. If you're on the vertical axis is logarithmic, you're going to get a straight line. if it's one isotope. But if you plot it on linear paper, you'll get correct readings, but it's going to give you a curve. Better way to do it is log paper, because after all, it is a logarithmic function. Remember, parallel lines in a decay curve, same half-life. The fraction decaying per unit of time is the same. This might be a hotter sample, this might be a cooler sample, but the half-lives are exactly the same. You'll recall we did graphical analysis here. Here was the proof. If this is 10,000 at time 0, at the half-life would go down to 5,000, over to the curve, drop a vertical, 5 days. This one is 5,000, we go down to 2,500, over, 2,500, we go over to the curve, drop a vertical, still 5 days. The half-lives are the same. You'll recall from the previous lecture that we said that the activity at some future point in time, we're going prospectively forward in time. We simply take the initial activity and multiply it by 1/2 to the power of n, where n is the number of half-lives. A very simple formula, much easier than e to the minus lambda t. Nobody likes working negative natural logs on a calculator. It's not simple. This is a piece of cake here. 0.5 to the power of n. Very simple. And you can work all half-life problems with that. Now, going retrospectively in time, we doubled it. So we went from 2 to 2 squared, that's 4. 2 cubed is 8. 2 to the 5th is 32. 2 to the 8th is 256. Going backward in time. Now, let's take a look. Let's guesstimate the answer to this problem. You can't work it in final form without a calculator, but let's take a guess. You know, we have a reading that was 20,000 counts per minute. 14 hours later, it's dropped to roughly 15,000 counts per minute. So you would predict that that's a half of a half-life. If it had gone from 20,000 to 10,000, you would have said, okay, the half-life is 14 hours, but it only made it halfway down. So thinking linearly, you would say, okay, if if it dropped from 20,000 to roughly 15,000, that's about half of a half-life. That's a linear extrapolation. So if 14 hours is half of a half-life, then 28 hours is our estimated whole half-life. And I'm not going to grind through the math, but when you work it out, it came out to 30. Our estimate was 28. Pretty good guess. We're within 10%. By graphical analysis, if you only had these 2 points right here, here's 20,000, here's 14,500. Simply extrapolate this straight line. You're on logarithmic graph paper. Go here to this where it intersects the 10,000 point and drop a vertical. And right there, 30 days, right on the money. How about this? True or false? After half of a half-life, 75% remains. Now that sounds good. You know, after one half-life, you got 50%. After 0 half-lives, you got 100%. So after half of a half-life, it kind of sounds logical that 75% remains. True or false?
False.
Totally false. This is a logarithmic function. And all you have to do is punch in on your calculator 0.5 to the power of 0.5. That's a half of a half-life. And it doesn't give you 0.7500, it's 0.7071. So a half of a half-life takes it down to 0.7071. Let's see if there's anything else here. We hold radioactive waste for 10 half-lives before discarding it. What fraction remains? So it's simply going to be 1/2 to the power of 10. 0.5 to the power of 10. If you punch this on your calculator, it's going to be 0.000976, or if you take out your trusty little fingers, it's going to be 1 over 1,024. Bottom line is that after 10 half-lives, we have reduced the activity to only roughly 1/1000. That means 99.9% is gone after 10 half-lives. It's only less than 1 part in 1,000. So if there's 1 part in 1,000 after 10 half-lives, then after 20 half-lives, it's going to be 1 part in 1,000th of 1,000th. That's a millionth. 1,000th of a millionth is a billionth, and 1,000th of a billionth is a trillionth. So every 10 half-lives reduces it by a factor of 1,000. Now remember, this is a rounded off number. It's not really 1 times 10 to the minus 3. It's really 0.0, sorry, it's 0.976 times 10 to the minus 3. Oh yeah. One last thing, and then we'll see if you have any more questions. And also, for the math lesson for next week, if there are any other topics like these that you would like for me to review, please send me an email or have your instructor send me an email, and I'll be happy to put that on the list. And assuming we have time, we'll review any topics that you would like to review. And if we run out of time and there are still more questions, I'll make you an offer that you can refuse if you would like. That is, I will give you an extra class on April the 1st. I know you're on spring break then, but if you really are interested and are willing to give up 2 hours or an hour of your spring break, we can have a class then if needed. So here's the last thing I want to review for today, and then we'll stop. This is bi-exponential decay, and you know that because even on a logarithmic scale, it's not one straight line. We have a straight line coming down here and another straight line coming down here. So what this is 2 separate isotopes. And the way that we work this is to simply ignore this piece here where they're interacting with each other. And so we'll say, okay, if this is 10, we'll go down to 5 and go over to the curve. And that will give us 4 bars. That's 8 days. That would be I-131. And this one here, the best thing to do is extrapolate it back to time 0. That's a 3. We come down to 1.5. That intersects at 60 days. And there are the lines that you would have drawn to work the problem. And here would be the answers. No one will give you an I-125 problem today. They would give you a different half-life that you should know. But that's how you solve the problem. Okay, it is exactly 11 o'clock. Any questions from anyone about anything? Any requests for next week? Anyone? Okay. If not, then I've stopped the screen sharing, and let me just modify one little thing here for a moment. And so I can see who's there. Okay, good. Okay, then in that case, I'm going to thank you again for your attention. Hopefully that cleared up some questions that you had. And I'm going to end the session for today, and I will see you next Thursday at 9 a.m. So have a great week. Bye-bye.
Thank you.
Thank you.
You're very welcome. Bye-bye.